Hello and welcome to the screencast where I'll be doing some examples of using integration by substitution. And in this video I want to focus on doing indefinite integrals with substitution. And so we're going to start with one of the most basic forms, and you might look at this and say, well, the integrand here is a polynomial. We could multiply that out and just find an antiderivative. Remember, this indefinite integral notation is saying find the most general antiderivative for the function 2x times the quantity x squared minus 1 raised to the fourth. But boy, I don't want to multiply that out. So let's see if we can be smarter about this. So I want to let v equal x squared minus 1. And then, so I'm looking at this, and I'm seeing an inside function here that's x squared minus 1. And I like to mix it up and not ascribe any specific meaning to variables, and so I don't like to use u necessarily when I'm doing these. You can use whatever variable you want for your substitution. It's just a dummy variable. But so I'm seeing this inside function, and I'm seeing its derivative lurking out here. And that's, remember, when we look at the statement of how we integrate by substitution, it's an inside function and the derivative of that inside function lurking around outside. So then, working in terms of our differentials, we say, aha. So we might even rearrange this first. And so I'm looking here, and I'm seeing that this part is just my differential dv, and this part in the parentheses is what I'm calling v. So I can rewrite this and say, well, this is v to the fourth dv. Well, v to the fourth is a function that we know an algebraic antiderivative for by undoing the power rule. We know that the most general antiderivative for v to the fourth is 1/5 v to the fifth plus our constant of integration c. We're not done yet because the original integral asked us for a function that of x, and right now we have a function of v, so we're going to use the fact here that v is equal to x squared minus 1 and finish up here by putting that in. Now let's check our work. So we should be able to differentiate this answer that we've come up with. Right, this is saying, give me the most general antiderivative for this function. So if this we're claiming is an antiderivative for our original integrand, we should be able to differentiate this and get back what we started with. And so we differentiate, and the power rule pops down to 5, which cancels with the 1/5. And so we have x squared minus 1 to the fourth. And then the chain rule says we need to multiply by 2x. And we can rearrange that so it looks just like what we started with. Okay, so let's look at another example here. And so again, we're seeing cosine with an inside function lurking in here. And so let's take t to be x cubed plus 2, because we see, well, okay, so dt is 3x squared dx. Well, wait, we've got x squared dx, so we can do a little bit of algebra with this, and we can say 1/3 dt equals x squared dx. And so let's go to work rearranging this now. And so now we see we can put our t in here. And then we've got x squared dx, which we worked out here and figured out that that's 1/3 dt. Now I'm going to take this constant and use our constant multiple rule for integrals and pull that past the integral sign. And now we're saying we need the most general antiderivative for cosine of t dt. And we know that that's sine of t, plus we need a constant out here. And now we asked for a function of x, and right now we have a function of t, so we need to put in that this is sine of x cubed plus 2. And you can check, I'll leave this to you for practice, go ahead and pause the video, take the derivative of this function and make sure that you get x squared cosine of x cubed plus 2. That's the great way to double check your work when you've done an indefinite integral, or anytime you think that you've got an antiderivative. Go ahead and check it by differentiating. Okay, so this one looks a little bit more interesting. But we think about like inside function. What's our inside function here? Well, we do see a function, sine of u, and its derivative, cosine u, lurking here. So let's try x equals sine of u, then dx equals cosine u du. Oh, hey, x is sine u, so this is the integral of x, and then cosine u du is dx. So this is saying integrate x dx. Well, we know the most general antiderivative for that quite quickly. That's a polynomial. And then we've got to come back. We were asked for a function of u. Right now we have a function of x. So we'll put in our x equals sine u, and we'll have sine of u squared over 2 plus a constant. Let's look at another approach to this. So we have this trig identity that says sine of 2u equals 2 sine u cosine u, which for our interest right now would say that sine of u cosine of u equals a half of sine of 2u. So we could also rewrite this integral and say that that's equal to 1/2 sine of 2u du, rewriting the integrand. And then we can go after an antiderivative for this guy, here letting t equal 2u, and so dt equals 2 du, and so du equals a half dt. So this then becomes the integral of a quarter sine of t dt. And we know an antiderivative for sine of t is going to be cosine of t with a minus sign in front of it, because when we differentiate cosine, we get a negative. And then we started with a function of u, we've got a function of t, but we know that t is 2u. Huh. Okay, well now we look like we've got two different functions here. I'll leave it to you to think about how you can use some trig identities to actually explain why these two things are equal, although it may come down to that constant being a little annoying, but certainly they'll both give you the same derivative. Okay, one more example here. This one gets a little bit fancier even. Okay, I'll relent and I'll use u for my variable and my substitution this time. We're looking at this and we are seeing some things that look close to a derivative up there. And you might be tempted to try just being u equals the e to the 3x squared part here, but when you can throw a constant in with it, you might as well, because it's going to go away when you work with the differentials, which is generally a good thing. So then we get du equals the 1 has derivative 0, e to the 3x squared, chain rule says times 6x, and then we need our dx. That's not quite our numerator, but we can move the 6 over to the other side, And then we do see x e to the 3x squared dx up there, and that's our 1/6 du. So this integral becomes, we've got 1/6 du over u, pull the 1/6 out front, and we know an antiderivative for 1 over u. If we don't like it written that way, we can write it this way. We know an antiderivative for 1 over u. It's natural log of u. And then we want the most general antiderivative, so we need plus our constant. And again, we need to be in terms of x. So we're going to come back here and we're going to have natural log of u was 1 plus e to the 3x squared, and then plus our constant. Okay, so there's several examples of ways that we can use substitution to undo the chain rule when we are calculating integrals.